Hello and welcome to the 39th lecture. So the content of the course is covered, and now that that's done, the only thing to do is to review and get ready for the final, which is cumulative, which goes over all topics. The review material that we have posted for you consists of past midterms, quite a number of them already there. So it's going to be impossible for me to work through all of them. I'm going to go through various questions I've just selected, which might be things you are somewhat rusty on. Volumes we spent quite a bit of time on. Hopefully, this is a solidly learned topic for you, and you'll have no problem with that. Expect it to come up quite a lot in the final. So I'm going to be going back from topics from quite a long time ago. You should certainly do the same. Expect questions from any part of the semester. So make sure you can do these kind of questions. The best way is to work through these past exams, make sure you can do these questions fluently without problem, and I will give you some examples in the next hour or so. So let's just go into it. So we have this question. This is question 7. I've forgotten from which midterm. This is our question. So we want to calculate the limit. So I'm just going to write find okay, so solution. This is actually a L'Hopital rule type question, because if we look at this as x tends to 0, this thing is tending towards 1, and this thing is tending towards infinity. So this thing is testing L'Hopital, and it's in the form of 1 to infinity. And L'Hopital's rule is where we have to kind of battle about two things in play, and whichever one tends to its limit faster determines what happens. So if we tend fast enough to 1, then the fact that we're going to infinity here will mean that the answer will be something like 1. Conversely, if we're not tending fast enough to 1, and this thing is going up to infinity faster, then we will be blowing up towards infinity, right? So review this topic. This is L'Hopital's rule. This was the final form we had to learn. And the main trick is the trick which we know whenever we see something of the form a function to another function, and that's to take natural log. So let h of x be the natural log of this thing. Okay, my properties of natural log. This is this. And instead of working out what this limit is, we're going to work out what the limit of h is as x tends to 0. Once we find out, we can unwrap it by simply inserting that into E, right? Because h is just log of the thing we're trying to study. So if we look at this, the limit as x tends to 0 of h of x, then this is the limit as x tends to 0, 0 plus of log of 1 plus 2x over x. And we know, of course, the graph of log looks like this. Yeah. So as we approach 1, then log of 1 is 0. So this is tending towards 0. The bottom is also tending towards 0. So we have 0 over 0. So as L'Hopital's rule forms 0 over 0. And then we can just differentiate the top and the bottom. If we differentiate the top, we're going to have 2 over 1 plus 2x. And if we differentiate the bottom, it's over 1. And now we take the limit as x tends to 0. Plus, and then we're fine, because this limit definitely does exist. The bottom is just 1, the top is just 2 over 1 plus 2x, and this 2x is tending to 0, so this limit is just going to be 2. So we know the limit of h. The limit of h is easy, right? But now we have to unwrap it, right? So this is h, it's log of the thing we're trying to understand. So the thing we're trying to understand is just e of h, right? So it's just e h of x. And e is a nice continuous function. So we can pass the limit through. This too we discussed in composition of limits. Go back for this topic if you're unclear. Oops. is equal to this limit here, the limit as x tends to 0 plus of e to the h of x. And because e is continuous, we can pass the limit through the function and talk about the limit, talk about e of the limit as x tends to 0 plus of h of x. And we've learned that is just e of 2. And that's our answer. Okay? So the moral is, we see something like this. It's a L'Hopital's rule. Whenever we see something which is unclear what it will be as a limit because of some kind of competition between various factors, then it's a L'Hopital's rule. This is the form 1 to infinity. Yeah. And then the other thing to remember is whenever we see a function to a power of another function, we're going to not deal with it. We're going to take log, deal with that, and then find whatever we need to find, and then unwrap it by composing it with e. So it's been a while, but this is a very routine example of applying L'Hopital's rule to this kind of form. So look back at this topic, make sure you feel okay with it. Okay, let's do question 9 from the same midterm. And it is asking us to use linear approximation to estimate, this number, the square root of 24.97. Okay, so solution. What is this stuff about? Well, I have a nice picture here. Let's erase it though. Linear approximation is about using the tangent line to understand a difficult function with instead its tangent line. So I'm going to draw a very similar picture to what I just erased. So the function we're going to consider is the square root function, which is a difficult function for us to calculate when we have some kind of decimal expression like this, right? So this is a square root function. It looks kind of like this, right? And what we're interested to do is to understand it at some value which is very close to 25. So let's take 25 right here. And if we take the tangent line to the square root function of 25 on a very straight tangent line, let me do that again. Damn it. Somewhat better. So we take the tangent line to the function of 25. Then if we take a value which is very, very close to 25, just put a little bit beneath it, then the difference between the value of the function at this number, a little bit less than 25, and the value of the function of the tangent line is incredibly, incredibly small. It's so small I can't even show it on this picture, right? That's the point of differentiability. That's the point of a tangent line. Is that locally we do an incredibly good approximation to our function with a linear function. Yeah? So what we're going to do is exactly that. We're going to calculate the tangent line to this function at 25. Yeah? And instead of trying to calculate this thing, we're going to plug in this number, 29 point, well, we're going to plug in this number, 24.97, into our tangent line, and that thing is going to allow us to get a very good approximation to what this actual value is. So, first thing to do is to find the tangent line. And we need to differentiate the function. So, f of x, as you know, is 1 over 2. X minus 1 over 2, if we apply just x is equal to 25 to this, because we're going to do the linearization around 25, so we need the slope when x equals 25, right? 1 over 2, and it's 1 over the square root of 25, which is 1 over 2 times 1 over 5, which is 1 over 10. Okay, so the slope of this red line is 1 over 10. And then in this topic, we call the linearization, we call the tangent line the linearization. So I normally call it T, and now we're going to call it L. So L of x. is the slope, x minus the x-coordinate, plus the y-coordinate. Right? And the y-coordinate is what we get when we stick in 25 into our function f. Square root of 25. Yeah? And that is going to be 1 over 10 x minus 25 plus 5. Now, we need to plug in this value 24.97 into this expression, right? Because, let me write this in the language of maths, we know that L is incredibly close to the function f for x near 25, right? And this value 24.97 is obviously very close to 25. So if you just plug that in, so L of 24.97, what's that? That is 1 over 10. And then we have 24.97 minus 25 plus 5. And then what is this thing? So 1 over 10. And this will be minus 0.03, because if we add 0.03 to this, we get 25, right? So plus 5. Should we keep it over here? No, let's move over here. So then this is 1 over 10. And what is this? This is, so if the 3 was here, if we had minus 0.03, it would be 3 over 10. But since it's here, it's going to be minus 3 over 100. Yeah. Plus 5. So what we have is minus 3 over 1,000 plus 5. Let's put it back in the decimals. So that's minus 0.00. That's 1 over 10. That's 1 over 100. And then this is the digit 3 plus 5. And then it's going to be 4.997. And that's the answer. Okay. Oh, I should be telling you what multiple choice answers these are. So in the first one, this was E. And in this one, it was D. Okay, so what did we do? Well, we remembered what the general idea is, that we're trying to approximate a difficult function, which is the square root function, with its linearization, i.e. its tangent line. So we simply calculate the tangent line around the point where we want to linearize, which will be a point very close to this number, but it'll be an integer number. It'll be something which we can easily calculate, and 25 is the obvious choice. Huh? So that's what we do, make this calculation. And then we remind ourselves what we're actually doing. Well, the principle is that the linearization is very close to the function for numbers close to 25. So we just plug in this number close to 25 to the linearization, and then we just do the calculation. We get out this answer. Cool. Question 5. Suppose for all x in the interval 0, 2, we have the following inequalities. Minus 2x plus a is less than g of x, which is less than x squared minus 4x plus 5. For what values of a? Oops, of little a. Can the squeeze theorem be used to compute the limit as x goes to a of, oops, as x goes to 1 of g of x. Okay, so this is obviously a question testing the squeeze theorem. We're going to start by drawing pictures to understand this information. And what we expect to find is, well, what we are given here is that we have a linear function which has got a slope of -2. So this is a, and it's got a negative slope of -2 like this. And that is underneath, or at least from the range from 0 to 2, this quadratic function, and g is trapped in between the two. So we could put the information that this is underneath the quadratic function by sort of putting a quadratic function like this. Yeah. But if the squeeze theorem is going to work, I mean, if the squeeze theorem is going to be applicable, then it must mean that this quadratic here has to squeeze g around x equals 1, which means that this function has to touch this function. So if 1 is here, say, then what we must have is that this quadratic function actually touches this linear function. So this quadratic function must touch this linear function like this, and just touch it. This quadratic function is not going to go through this linear function. It's got to just touch it, and then it's like going to go and be a curve up like this. Okay, that's what's got to happen in order for this question to make sense. Okay, that is what we expect. Okay, so this is the function x squared minus 4x plus 5 in red, and this function here is minus 2x plus 5. All right, so how to solve this? Well, what does the picture tell us? The picture tells us that, oops, plus a, is that this function has to agree with this function at a, right? And that is pretty simple to figure out, right? Start again. This function has to equal this function when x equals 1. When plugging x equals 1 into this, we just get some number, right? So there is some specific number such that when we plug x equals 1 into this, it will agree with that specific number. And then we can figure out a from it, and that will be all we have to do. Yeah, because they've given us exactly where the function g is being squeezed between these two, enough to apply the squeeze theorem. So g is some function here trapped between the two, and this whole theorem makes sense because there is nowhere for g to go when we consider the limit as x goes to 1. So if we blow up this picture right here, so imagine this is a kind of a magnifying glass taking this picture and blowing it up to something of size like this. Then what we see is this linear function like this, and then g is doing whatever, something. The quadratic function is coming in like this and squeezing it. Not doing a good picture today. And squeezing it. So there's nowhere else for this function to go. So g is forced to some specific limit by these two things that trap it. So this is the quadratic, this is the linear function, and this stuff has to occur when x equals 1. So this is above x is equal to 1. Yeah, that is what we have. That's if you understand the squeeze theorem, and that is the situation we have. All we've done is use this language that describes pictures to draw the pictures, remember what the squeeze theorem says, and then we have a clear prescription of what we have to do, right? So this is only possible if at x is equal to 1, this quadratic, x squared minus 4x plus 5 is equal to minus 2x plus a, right? But we just put in 1x equals 1 then. Yes, right? i.e. 1 minus 4 plus 5 is equal to minus 2 plus a. And then what? So that's going to be minus 3 plus 5, which is 2. And that's minus 2, which implies a equals 4. And that's it. Cool. A more interesting question would have been if they didn't tell us where we were going to use the squeeze theorem to squeeze G, just that there was some point and some point between 0 and 2, for example. And we would have still been able to answer that question. It would have been a lot tougher, a bit tougher in that case. But okay, but since they told us where we're going to squeeze, let's just use the information. Let's not work harder than we need to. And this question, again, hopefully fairly straightforward. That is the multiple choice option C. Okay, let's do another one. This is question 5. Oh, I guess from a different midterm then. Okay, this is another question 5. So we have the following. Let f prime of x be bigger than 0 and f double prime of x less than 0 on minus infinity to infinity. Which of the following is false for f? So this is a conceptual question, testing our understanding of these concepts. So the first thing we have to determine whether or not it's true or false is that f prime of x is decreasing. Is that true or false? Well, let's take a look. So we have that the second derivative is negative for every x between minus infinity and infinity, right? What is the second derivative? It's the derivative of the first derivative, right? So if we have the derivative of the function is negative over an entire range from minus infinity to infinity, that function is decreasing. That means the slope is negative forever, right? So that has to be a decreasing function. So the derivative of f prime is negative, therefore indeed this thing is decreasing. So this is not false, it's true. Okay, so that's not the false statement. Next statement. F is C down. F is indeed C down because C down is exactly having the second derivative negative, right? C down is like this. It's curling underneath its tangents, yeah? And as you can see, if we have something which is curling underneath its tangents, then the derivative is decreasing, the second derivative is negative, and that's exactly what we have. So that is true as well. So that's not a false statement, yeah? Next statement. And these are not I, these are A and B. A, B, C. Of 5 minus oops. Okay. Notice the way that they phrase this question. So 5 minus 4 is just 1, right? 4 minus 3 is just 1. So they could have just written f of 5 minus f of 4 bigger than f of 4 minus f of 3. But they write it in this form because they're trying to bring to mind for you one of the theorems we studied, which is the mean value theorem, right? So let's draw a picture. If we have some function f, okay, our function is actually decreasing. Oh no, I'm sorry, this is an increasing function. The second derivative is negative. So it's an increasing function. The second derivative is negative, so let me try and draw this. kind of like this, yeah? And then what is this thing? F of 5 minus f of 4, we have 5, and say this is 4. Then this number right here, f of 5 minus f of 4 over 5 minus 4, is the slope of the secant line connecting these 2 points, 4 f of 4 to 5 f of 5, right? Yeah. And the mean value theorem says that there must be some point between 4 and 5 such that the derivative of f is equal to the slope of the secant line, right? So this is trying to bring to mind to you the mean value theorem, yeah? So there must exist, again, some point between 4 and 5 such that the derivative is equal to the slope here. So let's write that down. So exists say a between 4 and 5 such that f prime of a is equal to this slope, f of 5 minus f of 4 over 5 minus 4. Yeah? And in the same way, if this here is 3, then let's change colors. Then this point here is 3f of 3, and this is the secant line right here, right? And so there must exist, put over here. Yeah. So this statement here has to imply that for these numbers b between 3 and 4 and a between 4 and 5, we've got to have that f prime of a is bigger than f prime of b. Yeah. However, what we know is that f prime is decreasing. Yeah, but a, since it's between 4 and 5, has to be bigger than b, which is between 3 and 4. So this is not decreasing. So contradiction. That f double prime is less than 0, and that, well, let me say because, that means because that implies f is decreasing, or f prime is decreasing. So indeed, this is false. This statement is false. So C is false. Okay. So the hint of what you should apply should again come from the structure of this. Yeah? And what should have come to mind is that this thing is asking you to apply mean value theorem. Yeah? And if you do that, then you come up with the fact there must exist some a in the interval from 4 to 5, which is equal to this number, and some b in the interval from 3 to 4, which is equal to this number. Yeah? So therefore, the gradient must be increasing as it goes from b to a, because b is less than a. But the gradient is actually decreasing because the second derivative is negative. So this is a slightly harder question, but again, it should be a question that was accessible, and particularly if you draw the picture, because you know what concave down looks like, right? You know what concave down looks like. Huh? So it's curling It's an increasing function, but it's getting flatter and flatter and flatter, right? So you wouldn't expect, as it gets flatter and flatter and flatter, this ratio to be bigger than this ratio, right? That's not consistent with the picture, so I haven't really made enough of a curve to see that clearly. Well, let me try and do a better curve. So we have a function which is increasing, but it's concave down. So it's flattening out like this. Yeah, it continues to increase, but it's flattening down. Yeah. So if that's the case, then we don't expect to have some interval which is further along will have a more steep angle than this interval which was earlier. Right? That contradicts the picture that we see. And that should give us the hint of what to do. The way to express that idea is the fact that we have the mean value theorem and then have that this thing contradicts our hypothesis. So it's a bit of a harder question, but it is a good question, and it's a kind of question that you should be able to get a grip on if you've been doing this stuff, if you've been learning to visualize this, looking at the pictures after you turn the math into the pictures and asking yourself, what does this question mean with respect to this picture? Doesn't look like it's true, and then further express that in the language of math. Cool, we have a couple more statements, which, I mean, there's only one false answer. Oh no, it says, which of the following is false? Usually there's just one, right? And since it's multiple choice, you can stop right here, see it's false, but let's just complete it. The next one is f is increasing. Well, it is increasing because this thing is positive, so f is increasing. That's true. And then E, f has no local extremas. Extrema is where we have a local max or a local min. That will only happen above a critical number, which is where the derivative is 0. The derivative is never 0 because we're given it's always positive, so that's true as well. Okay. Cool. All right, I'll erase the board and we'll do some more. Question 2. The integral from 0 to 2 of 1 over 1 plus x dx is the limit of what? Right Riemann sum. Sorry. Okay, solution. All right, so this is a nice positive function, so let's start to draw this picture. So when x is equal to 0, it is just 1, and then it decreases, so it's like 1 over 3. When we're here at 2, so it kind of goes like this. Something like this, say. Yeah? And what is this definite integral? Well, if it's a positive function, it's the area underneath the graph, right? And this was something we learned as something we understand by approximating this quantity, the area underneath the graph, by a bunch of rectangles that whose sum of the areas of these rectangles is more and more like this actual area, right? And what was the procedure? The procedure was we took the base here, we cut it up into n equal pieces, yeah? And then if this is my depiction of these n equal pieces. And then we defined a bunch of rectangles. And we defined the rectangle's height in terms of using the function itself. And we define its height either using the right endpoint or the left endpoint. If we do the right endpoint, we draw this picture up to this, right? And then go across like this. So the right endpoint approximation looks like this. So literally do this before you do anything else. So you remind yourself what is going on. Because again, this is a language to describe pictures. We draw the pictures first, then we use the language. Cool. All right. So with this in mind, we know what to do. We're going to have to cut up this thing into n equal pieces. We're going to have to define each of these intervals, and it's something we've done many times before. And then we're going to have to come up with an expression that gives the sum of all of these individual rectangles, and there'll be n of them. So let's do it. Well, if we have n of them and they all have equal base length, then the base length has to be 2 over n, right? So delta of x equals 2 over n. And then we're going to have to define these intervals themselves. So the first one will be x0, this one will be x1, this one will be x2, and so on. The last one will be xn. And each guy is defined from the last guy by adding delta of x. It just moves along by delta of x from the last guy, right? So x0 is 0, x1 is equal to x0 plus delta of x. x2 is equal to x1 plus delta of x, but because x1 is x0 plus delta of x, that's the same as x0 plus 2 delta of x. We've done this lots of times. So if we continue like this, we see that x3 is equal to x2 plus delta of x, which is the same using this formula as x0 plus 3 delta of x. And we continue. So then xi is equal to x0 plus I delta of x. This is the general thing which we do for any interval AB that we've cut up into n pieces. This is the way we define these xi that define these intervals, cutting the AB into n equal pieces, right? And this thing gives that xn is actually equal to the last number, which is just 2 in this case. Okay, so since x0 is 0, then all of this stuff simplifies. So xi is going to be 0, and then delta of x, we know what this is, so just 2i over n. Cool. So we know exactly what these things are. We know exactly what these things are. Cool. So now, taking things step by step, we're going to add up the area of each rectangle one at a time. So the first rectangle, so write this areas, let me write sum of areas of rectangles. What's the first one? The first one has got base length delta, and its height is the function applied to this x1. So delta of x, and then the function f of x1. And then the next one is delta of x, and then the function f of x2, and so on. And we keep going. And there's going to be n of them, so dot, 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 plus delta f, delta of x, f of xn. That is the expression for the sum of all these rectangles. So it's the sum. Now we're going to put in what the expressions are, right? I is equal to 1 up to n. We know that delta of x is 2 over n, and then it's the function, and then it's going to be 2i over n. Cool. And what is the function? Well, the function is this thing, right? So this is our function. F of x is 1 over 1 plus x squared. No, just x. So then we can just put it in. And it's 1 over 1 plus 2i over n. And that's the answer. Okay. If you verify what you're doing with the pitches at all the stages, then I hope you'll come to this and feel confident about it. And again, this is the kind of thing that if you try and memorize an algorithm, then you really come up with some strange things because yeah, it's just it just doesn't work too well. So please go through this, seeing this just for the first time in whatever number of weeks. This might be a bit fast. Play this again. Do questions of this kind. This is, I think, not a difficult topic. It's just a new topic for many of you, and you have to grab onto the pitches, and then you'll be fine, and then it'll make sense. Huh? So that's all we did. We just drew what we knew the Riemann sum to be. It's this bunch of rectangles. Yeah. We have to define them. We have to define, firstly, the base of each rectangle. Then we have to define what these xi are in order to define these rectangles, right? And then the general expression for the right approximation, the right Riemann sum, is this, right? Each rectangle is its base times the height defined by the right endpoint. That's what we've written here, right? Then we put in what we know the delta of x to be and the xi to be. And finally, we put in what the function is. Yeah? Cool. All right. Let's do another question. Okay, we'll do these two questions because they are kind of indicative of the tricks that can be played on you. So, question 6. Evaluate this integral from 1 up to e of -4 plus x squared over x to the 3 dx. Okay, so when we have integration questions, there's only two things at play. We either have the u-substitution method, or there has to be some elementary thing that allows us just to work it out because we can figure out the antiderivatives. And in this case, if we look at it for a little bit, we see that we can break this thing up, and it's the integral from 1 to e of -4 over x to the 3 plus 1 over x dx. And now that is something pretty easy because we can figure out the antiderivative of this thing, right? It's going to be 2x to the -2. Yeah. And then this thing over here will just be log of x. And then we just put the we can just put the numbers in. So we're going to have 2 over e squared here. And then log of e is just 1, and then minus 2, and then log of 1 is 0. So it's this. So it's 2 over e squared minus 1. So that's not hard. No? So when I first looked at this, I was thinking, oh, it's some kind of tricky u sub, but no. It's just breaking this up. So it's easy to make that mistake. It's easy to just launch into something without noticing something which is just reducible to an easy problem by some algebra. So before you try anything, make sure that isn't the case. Now let's do this question. I think it's question 7. And now it's this integral. Okay. So this time, there isn't any easy algebra, as you notice pretty quickly. So then it's the only other thing we can do, which is u sub, right? So a u sub, we're looking to make some part of this be u, such that when we write this du as something times the dx, we pick up the something times the dx as well inside this, so the entire thing can get turned into u. Yeah? That's the strategy. And if you've done enough practice with this, what you come up with pretty quickly is that if we let u be this stuff in the center, this stuff in the denominator, 1 plus x squared, then we're in good shape. So put it here. Let u be 1 plus x squared. Then du by dx is just 2x, which implies du over 2 equals x dx. Yeah? And it's a definite integral, and we're going to do this just by changing the limits in terms of u. So then let's call this thing star. So star is equal to, so when x is equal to 0, and we put it into this thing, we just get 1. Oops. No, that's correct. We just get 1, and then when x is equal to 1, we put it in this thing, we get 2. This x dx we figured out is du over 2, so let's put this 1 over 2 outside here. And then this thing just becomes 1 over u du, like this. Oh, sorry, 1 over u squared u. Now we're good, because this is an easy thing, right? So the antiderivative of this thing will be minus 1 over u, yeah? And then we just put the numbers in, so we have 1 over 2. Let's put out the factor of a half. And then we're going to have 1 over 2 minus 1, yeah? And then that's going to be minus a half to minus a half, which is 1 over 4. And that is the answer, which is answer C. And this other guy is answer B. Okay. One more question. Question 8. Find the minimum distance between y is equal to minus 2x plus 5 and 0, 0. And that's the entire question. Okay, so we start by drawing the picture as normal. So what does this look like? So we have intercept of 5, it's sloping down like this. Yeah, and this is 0, 0. Okay. I can see straight away two ways of doing this. One way, well, when we have 2 ways, we can check they both agree. So we know that the slope here is minus 2. We also know that if we have the closest point to 0, then it's going to go like this, and it's going to touch this at a right angle, right? So since the slope here is minus 2, as we learned, then the normal line to this line is going to have slope, which would be minus 1 over the reciprocal of it, which is going to be a half, right? So we saw this by drawing triangles. Look back at that lecture on normal lines. I think it's in the lecture on tangent lines and normal lines. So this thing has to have slope a half. Okay, so this point right here, which is the closest point, will be the point where this line intersects this line. And this line goes through 0 and has a slope of half, right? So find x such that a half x is equal to this thing. Yeah. And then what's that? Let's multiply everything by 2. minus 4x plus 10, which implies that x is equal to 2. And from this formula, if x is equal to 2, this implies that y is equal to just 1. So then this point right here will be the point 2, 1. And then so the distance will be the distance from 0, 0 to 2, 1, which by Pythagoras will just be the square root of 3. So here's the square root of 1 squared plus 2 squared, which is, is that right? 2 squared, which is 4. 1 squared plus 2 squared. So it's not root 3, it's root 5, right? It's root 5, which is square root of 5. So that should be the distance. Now, let's do it a different way. Okay. A different way to do this is to use the fact this is an optimization problem, right? So we have this line, right? Let's draw it again. Yeah, and every point on this line is given by x, and then the y-coordinate is given by this, minus 2x plus 5, right? So if we want to understand the distance between 0 and any point on this line, which is coordinates, is given by this, as x ranges from minus infinity to infinity, let's instead understand the distance squared, yeah? And then that'll just be a function of x, so let's write d of x. And then what is the distance squared, like Pythagoras? So if this is our point right here, it'll be the x-coordinate squared plus the y-coordinate squared. Right? So it's going to be x squared plus minus 2x plus 5 squared. Yeah, it's the distance squared. Let's clean that up. That's x squared plus 4x squared. It's going to be times this, but there's two of them. Right, this. So minus 20. And then plus 25. So that's going to be, let's factor out 5 straight away, 5x squared minus 4x plus 5. And that is the distance squared. Oops. Ouch. Okay. And we want to minimize it, right? So as we range over all the x's, we want to minimize this thing. We just take the derivative to find the critical numbers. So d prime of x is equal to 5 times 2x minus 4. So d prime of x equals 0 implies that 2x minus 4 equals 0, which implies that x is equal to 2, and which is what we got before. And then by the fact that we're on this line, where's the form of the line? So y is equal to 1, and we have exactly the same coordinates, 2, 1, so distance. is again by Pythagoras the square root of 5. Yeah, let's make sure that's multiple choice option given to us. Yeah, which is option E. So both methods, which are completely different, give us the same answer. So we are happy. Yeah? And what did we do? Well, we drew the picture first of all. Our first approach was just using the fact that the picture told us that the distance from the closest point on the line to 0, 0 is just going to be the length of this line right here. Yeah? And we can easily find that if we can find this coordinate, but we know what this line will be because we know what the slope is, right? Because it's the normal line to this line, so it's slope a half, so we just solve this. Pretty easy, quick calculation. Second approach, perhaps more using what was intended for this question, which is optimization. Express the quantity we're trying to optimize. We're trying to minimize the distance, huh? But we did it squared because we don't want to deal with square roots. We're trying to minimize the distance squared, it's just in terms of one variable, right? Because every single point here is given by x and then minus 2x plus 5, right? So in these optimization problems, often you have this optimization, it's in two variables and there's a constraint, and that turns the thing you're trying to optimize into something of one variable. We just did this in one step here, saving time and board space. So then this thing is our expression that we're trying to minimize. It's a nice quadratic, you know. So then we can find the critical number. It's this thing. I didn't bother to check that it's actually minimizing because from the picture, it's clearly going to be minimizing. If this was a free response, you'd have to point out why this is the minimizer, not the maximizer. But for your own, since we're just trying to find the point, it's clearly the minimizer because if we look at this function as x blows up, I mean, as x increases, this quantity blows up, right? So this is, in fact, it's just a quadratic, right? So the quadratic shape like this and the one critical number it has will indeed be the absolute minimizer, which is the thing we're looking for. So that's why we felt safe that x equals 2 was actually the thing we wanted. We put in x equals 2 into our formula for the line. We got y equals 1, and it's the same kind of stuff. Okay, always good to have more than one method to get the answer, particularly to check against small errors. So this is just a kind of a collection of questions that I wanted to go over, given the amount of time since we worked on these things. This is what I suggest you do. You look at these past exams, you go over and do all of these questions and make sure you can do them. Just make sure you're fluent with them. If you are able to do that, and if you've learned volumes solidly, you should be in good shape. If you've done the preparation, as many of you have learned, going from test 2 to test 3, there was many students that a significant jump in score. It is just a fact of your preparation. That's all that this course is testing at this level. It's not testing your innate ability in any way at all. It is testing your preparation, your self-discipline, your ability to work consistently. And if you do that, then this will not be a hard exam for you. You will do well in it. So many of you, which had this big boost from test 2 to test 3, keep that momentum. You now know what happens when you work much more consistently, put more time in, prepare more. Just keep doing that and you'll have the same effect. Those of you who haven't seen such an effect, just trust me, that's what's going to happen. You have 4 days, 5 days left, 4 days left. So keep working, keep going through these questions. Don't lose momentum. The semester's nearly over, and good luck to you on the final exam.